Let's continue with 5.7 notes. One thing that we're going to have to do is we're going to have to use completing the square method in order to rewrite the denominator of some of our problems so that we can match it better with the inverse trig antiderivative rules that we learned from the previous page. So let me review some of these steps for completing the square. So the idea is the reason why we complete the square is so that we can put something in the form of a trinomial into a form that is a binomial quantity squared. So what we're trying to do is we're trying to find the constant value that will allow this trinomial to be factored into a form that is a binomial squared. So we first need to have the form x squared plus bx plus c. Next step is we want to add the spaces to indicate that we're looking for a value that will cause this to factor out nicely. So I'm going to just have that constant out to the side. The value that we're looking for, whatever value we find, we have to make sure that we also subtract that value, because we don't want to change the expression of we don't want to change the value of this expression. So if we do plus 9 here, we also need to have a minus 9 here. So that way, when everything is said and done, it's we've maintained balance on this for this expression. Okay, and the way that we find this missing value here is going to be the coefficient in front of the x divided by 2 quantity squared, and that will go in both spaces. Once you do that, then we can just factor and we can continue on with the problem. Okay, let's look at example 4. We have the integral of dx over x squared minus 6x plus 13. It's not very apparent that this will match our antiderivative rules, because we don't see a squared and the u squared, even though without the square root it looks like this would match the arctangent rule if we can get the denominator to match in form with the rule. So let's try and complete the square for the denominator, see if we can get this to show up as a different form. So x squared minus 6x plus space plus 13 minus the space. And we're trying to maintain balance here, so that's why we need 2 spaces here. So the value that we put in the space is b over 2 squared. Now our b value is 6. 6 divided by 2 is 3. 3 squared is 9. So we put 9 in both the spaces. So we have x squared minus 6x plus 9 plus 13 minus 9. Now when we have this, we see that this factors out nicely to be x minus 3, x minus 3. So we'll write this as a binomial square, so x minus 3 quantity squared. 13 minus 9 reduces to be 4. So we have something now that looks a little bit better, a little bit more like the rule that we saw with the inverse trig antiderivatives. Now, if you look at this form and compare it with the arctangent rule, you see a lot of similarities, right? We see the squared here that matches with the squared here, but we also need the exponent to show up for the 4. So I'm going to write it as x minus 3 quantity squared and 2 squared. So now this matches nicely with the arctangent rule. We know that the u value is always going to have a variable as part of it. So our u value is x minus 3. Okay, whatever is inside the parentheses, and our a value is what's inside the parentheses is 2. So we have our a value is 2, our u value is x minus 3. We find the derivative du over dx is 1, dx is du. We went through u substitution. There's not any coefficients that's produced. So it's simply integral of du. Dx gets replaced with du. A squared plus u squared. This matches perfectly with the arctangent rule, so we follow the rule exactly. 1 over a arctangent of u over a plus c. So we have our a value, we have our u value, so we simply plug all that in. A value is 2, u value is x minus 3. So we have 1/2 arctangent of x minus 3 over 2 plus c. Okay. All right. Complete the square method only works when there is no variable in the numerator. Okay. If so, we have to look to other methods, or we may have to combine with other methods, and we're not able to rely simply on these inverse trig antiderivatives. So just keep that in mind. And that's going to come into play as we look at example 5. Okay, so example 5, we have the integral of 2x minus 5 over x squared plus 2x plus 2. Okay, if you look ahead, we can't split this up. We're not going to be able to use synthetic division. Use substitution won't work either. But let's see if this will match with, if we complete the square, if that will get us anywhere. So denominator, we're going to create the spaces here. B value to fill in the space, it will be b over 2 squared. So 2 over 2 is 1. 1 squared is 1. So we'll put a 1 inside the spaces. Now, looking at these three terms, we're going to factor. This factors out to be x plus 1 times x plus 1, which is x plus 1 quantity squared. 2 minus 1 is simply 1. So we have, after we complete the square, we have 2x minus 5 over x plus 1 quantity squared plus 1 dx. Okay. It's not going to quite work perfectly, but let's see if we can get anywhere if we just went through use substitution. And if we're needing to make any adjustments, we'll do that later. But let's see what we get if we were to go through use substitution. So we're going to let the u value be the denominator, the x plus 1 quantity squared plus 1. And if we go through derivative, we can go through chain rule here. So 2x plus 1 to the first power times the derivative of what's inside. So the derivative of x plus 1 is 1. And then this 1 goes to 0. So we can solve for dx. If we distribute the 2 through, we'll get dx is equal to du over 2x plus 2. Now, you look here, we have 2x plus 2, and we want this 2x plus 2 to cancel out the 2x minus 5. Okay. Now, we see that this does not currently match the numerator needed in order for us to cancel out. So what we can do is, the only thing that is standing in the way is some constant value, right? We can rearrange and split the equation to make our use substitution work. Okay. So let's say we make it so that our numerator is 2x plus 2. Okay. So if we have 2x plus 2, we also need to have a minus 7 in order for us to maintain the value of our original problem, right? 2x minus 5 is the same thing as 2x plus 2 minus 7. And if I'm adding these two fractions together, I'm going to get this value. And again, the reason why we want this 2x plus 2 is because we want this use substitution to work. Okay, we're trying to make some adjustments because we're restricted in our u value. But we can play and change the top to help us adjust to cancel out. So we already went through our u value. Our u value is x plus 1 quantity squared plus 1. We went through the derivative, and the derivative is du over 2x plus 2. We see the 2x plus 2 will cancel out nicely. Now the integral of 1 over u is simply natural log of the absolute value of u. And that will turn into ln of x plus 1 quantity squared plus 1. Okay, so that's the first portion. Now if we look at the second portion, the 7 over x plus 1 quantity squared plus 1, this matches nicely with the arctangent rule. So we can let our u value be x plus 1, our a value is 1, our derivative is for x plus 1, du over dx is equal to 1, dx equals du. And we can simply plug everything in. So the rule, we can take the 7 out in front. The rule is 1 over a, arctangent of u over a plus c. So 7 times 1 over 1, arctangent of u, and the u value is x plus 1 over 1. So we have this expression representing the antiderivative for our integral here. And we can simply combine and simplify. The x plus 1 quantity squared plus 1 reduces to be x squared plus 2x plus 2. And this is indefinite integral, so we need the plus c there as well.